It's a pity I cannot be there. I'd rather be over there, but unfortunately I couldn't rearrange my schedule so that I can be in India at this time. I hope it's going to be another opportunity. So this talk will be an introduction, and the first part's probably going to have some overlap with what David said in his lectures. But I want to set the stage so that, in a sense, we all on the same page. And I also want to, in a sense, set the more general setup, what gauge gravity duality is meant to be. And as we just discussed, just feel free to interrupt me at any point. So let's start from the very beginning. So the very beginning is the statement of holography, what holography is, in a kind of general abstract sense. So in holography, we have T+1 dimensional gravity. And this is meant to be equivalent in some sense to quantum field theory in the dimensions. And this was introduced about 30 years ago by Taft and Susskind. I think it's fair to say for the majority of the community, they were not this idea took off only after ADS safety, where there was an explicit realization. But to really understand what it means, I'm going to start really on the left-hand side, just describe a little bit the sort of things we want to know about quantum field theory, and then build our way to see how we could possibly have a realization of quantum field theory by using a different formulation, a different language, by discussing gravity in one dimension higher. Now, if we go again back to the very basics, one of the most basic observable, both classically and quantum mechanically, is if you have an excitation, you want to know what energy it carries, or it has a momentum, what momentum it has. So essentially, all quantum field theories have an associated composite operator, which is the energy momentum tensor, Tij. So for example, if you have Yang-Mills theory, T = 4, then the action for that theory is the usual expression associated with gluons. And then from here, you can work out the energy momentum tensor. The easiest way to do that is to couple the theory to a metric and then vary with respect to the metric. So the usual convention is to have a factor of 2 here, and then you differentiate this action where we have coupled this to a metric. And then we get so now if we want to know the energy of an excitation, so what we need to do is we need to integrate the energy momentum tensor over a Cauchy slice. We just take the 0,0 component and then we integrate. This is going to give us the energy. And if we want to know what is the excitation, what is the momentum, then similarly, there's a similar formula where you now integrate the Ij. Now, this operator is important not only because it covers, it describes the energy and momentum, but it's also a generator of, as we know, conserved quantities are associated with conserved currents, not the currents. In this case, the energy momentum tensor is the generator of space-time transformations like translations and that give rise to energy conservation and momentum conservation. And if you have conformal symmetry, then the energy momentum tensor is the generator of conformal transformations. Now, the theory could also have other useful observables, other gauge invariant observables. And this could be scalar operators. For instance, one can have what some people call the gluon operator, the trace of F square. And we can give a number to these operators, which characterizes them partly by just the dimension of the operators. And this is an operator of dimension 4. Or you can have operators with higher dimension, like F square square, or I, J, K, L, Li. So these are operators of dimension 8 and so on. Or we can have vectorial operators, which are symmetry currents. And if we want to know all the information is there about quantum field theory, what we want to know is we want to know the correlation functions. So quantum dynamics is encoded in correlation functions. Of such gauge invariant operators. So we insert the local positions, the number of operators with kind of different dimensions. So if we know the set of all correlation functions of all gauge invariant operators, essentially we know everything which is there to be known about the CFT. So now gauge gravity duality gives us a way to get access to this information by a completely different tool. So usually in quantum field theory in quantum field theory classes, we learn how to compute these objects in perturbation theory. We assume the theory is free plus a small perturbation, and then we use that in order to use Feynman rules of Feynman graphs in order to compute these correlators. Now, gauge gravity duality gives an alternative description of that. So if we are to describe this type of objects using gauge gravity duality, then the first thing we need to know is we need to know how to map the objects we are discussing to something on the other side. And for the objects I just discussed, so if you have the energy momentum tensor, then gauge gravity duality associates this to a bulk metric. If you have operators, scalar operators with dimension delta, this will be scalar fields with a mass which is associated to the dimension of the dual operator. And if we have symmetry currents, this would correspond to a gauge field in the bulk. Okay. Now, suppose you want to have, we suppose there is a duality. So if there is a duality, this means that for two theories to be equivalent, they have to share the same set of global symmetries. So now for generic quantum field theory, the global symmetry is Poincare transformations plus possible internal symmetries. And now under special conditions, so usually if you have a quantum field theory, this changes when you look at different scales. So there is a normalization group flow, and then the theory in the infrared typically becomes conformal. So we get the conformal group at fixed points, normalization group flow. So now this means that if we are to realize quantum field theory using a different description, we have to be able to identify how these are is realized on the other side. And then we have to have the same objects. And I described here how you see that you have the same objects. Now, in gauge gravity duality, so the way this is realized is, so now if you have a gravitational system, so global symmetries of gravitational systems are essentially the isometers of the background. So this means that if you have a gravity theory, then this has to have an isometer such that you realize the symmetries. And we also need to be able to see this transition, that there is a limit where the Poincaré transformations become conformal. So this means, first of all, to go back a step. So here we have associated, so we know that all theories contain an energy momentum tensor because typically excitations have energy and momentum, and this is what encodes those. So this means that if this is to have a dynamical description in one dimension higher, then you need to have a dynamical gravity. So you cannot have holography without dynamical gravity. Now, if you have dynamical gravity, this has to have a special property. So I should admit, so gravity, the gravity theory we're considering, should admit the so-called kind of domain wall solutions. Which take the following form. So that theory for a generic phi and A has the isometries, so it realizes Poincaré transformations. But if in addition, we have that as R go to infinity, A of R goes into R, and phi of R goes to a constant, then this metric has additional transformations. This becomes an I-de-Sitter metric whose isometries are the conformal transformations in one dimensionless. Okay. So that's the setup that we need. So now to move on, I think I'm going to describe in a little bit more detail what an I-de-Sitter metric is. David, did you cover I-de-Sitter in your lectures?
Yes, we covered I-de-Sitter in the sense that we gave the global metric and we gave the Poincare slicing in one coordinate system, which did not include this row this way. We basically used the standard harmonic form version, the limit of the original theory.
Okay, okay. So there will be a little bit of overlap, but I want to use this as a starting point for what I'm going to say afterwards. So
can I ask a question?
Yes, yeah, of course.
I did not quite get why you want these domain wall solutions exactly.
So you want the generic quantum field theory, the symmetry of the quantum field theory are Poincaré transformations plus possibly internal symmetries. So you want a gravitational solution which realizes Poincaré transformations. as isometries and has a limit where these transformations become conformal. And the unique metric that does this is this one. So this metric here for generic A of R, if you look at its isometries, are Poincaré transformations in one-dimensionless. And in addition, if this function A of R has the property that as you go to infinity becomes linear in R, then this metric here becomes the ADS metric. And then the ADS metric is precisely the isometries of the ADS metric are precisely the isometries in one-dimensionless. So that realizes this setup, but on the bulk. Yeah, clear?
Thanks.
Yeah, these xi coordinates are spatial coordinates, or it includes time as well?
In this coordinates, so here I'm using Euclidean, but if you want, there is a Lorentzian version by just weak rotating. So this one I can also write as minus. So if I want a Lorentzian, then that part would be in this format.
Thanks.
Actually, my next slide would be Lorentzian. Any other question? Okay. So other de Sitter spacetimes. Well, first, of course, these are solutions of Einstein equations with negative cosmological constant. So I will call the metric with capital G. Oh. So not to be confused with the Einstein tensor.
I'm asking a question which shows that I'm really confused. R goes to infinity is your boundary, right?
Yes.
But you wanted the boundary theory to be conformal at large distances. And I thought infinity represents short distances.
Yeah. So I want to start from a conformal point. So that's a good comment. So in the I will describe this setup a little bit more as we go on. But I want to start from a CFT in the UV. Okay. And then as I deform the CFT by adding relevant deformations, that becomes a generic one of field theory. Now in the AR, this may flow again to a CFT. So that would be described in the bulk with a transition where you go from one ADS critical point to another one.
Okay, so you haven't incorporated that. Okay, thanks.
I haven't incorporated that. So here I'm just starting from the UV where I have a CFT, and then I deform the theory. Okay, so again, under the de Sitter spacetimes, solutions of Einstein equations with negative cosmological constants. That these are the solutions with maximal symmetry. And the metric, which from what I've heard David already gave, in global coordinates is, and in Lorentzian signature is given by these coordinates. Maybe David gave it in slightly different ones, but this is one set of global coordinates. All other ones are equivalent. And then here, theta goes between 0 and pi over 2. So if you want to visualize this, this is like a can. So here, theta equals pi over 2 is the edge of the can, and then time goes upwards. So this has the property that if you send light rays, this is going to reach the boundary in finite proper time. So you really, this space-time really has a boundary. So now the issue is, so this is the space-time. I want to make sense of the meaning of the boundary. So the space-time has a conformal boundary. So the metric, so let me put here, this is space-time has a conformal boundary. And I want to explain what conformal boundary means, especially conformal. Now, if you look at this metric, if I try to put theta equals pi over 2, the metric diverges. So this means there is no induced metric at the boundary. However, there is a procedure that mathematicians developed in order to try to define an object at the boundary. So now you introduce a so-called defining function. Which I'm going to call R, such that has the following properties. So if you evaluate this function at theta equals pi over 2, this is equal to 0. Its derivative at theta equals pi over 2 is different than 0. And finally, if I evaluate this in the interior, this is positive. So I need to have a function with its properties. And if I have a function of that in these properties, then I can define a boundary metric by multiplying the back function with R squared, and then taking the limit theta pi going to pi over 2. Now, if you look at this metric, this has a second order 0 at the boundary, and this function R has a 0. This means that since I square it, this means this object has a limit. Okay, so now we got something. So there is a boundary metric that exists, but clearly this object here, depending on how I chose this defining function. Now suppose we use instead a new defining function, which is related to the previous one by an exponential. So now the exponential has no zeros and no poles. So this means this satisfies the same conditions. So this means I can define a new metric by following the same procedure. Oops. Using the new defining function. But now, since the two defining functions are related to each other, we get that the two boundary metrics that we get are related to each other by a conformal Eval transformation. So this procedure, so we defined a metric up to Eval transformations. So this object, this is called a conformal class. So what the ADS has, the ADS does not have a boundary metric, as a conformal class of metrics. Now you can let's think of an so let's apply this to ADS itself. So we can choose R to be just cosine theta, and then this procedure is going to give us the boundary metric, which is which is this one. So this is the Einstein universe. So properly, ADS has a boundary, which is the Einstein universe. Now the Einstein universe, it's easy to see that's conformal to Minkowski. And we just argued that the only object we can define using ADS is a conformal class of metrics, not the metric itself. So this means that any metric within the same equivalence class is as good. So instead of considering the boundary to be the Einstein universe, we can equivalently consider the metric to be just Minkowski space. So this gives, so now from here, so now choose as a representative of the conformal class the flat metric. So now in this parameterization, then we get the description I had earlier. I said earlier over here that if I take, I wanted to demand that as R goes to infinity, this A of R becomes linear, and then this metric element is just this one. And indeed, one can realize this by just changing coordinates in the bulk. So these are so this takes us to the to Bangalore coordinates, and we can also further change this. So if I consider further change of variables, I can write this in another way, which is commonly used. Which is this one. Okay, so, and that is going to be in a sense of starting point to kind of generalize this setup to go beyond ADS spacetimes. So any questions up to this point? Okay, so now we define what is an ADS metric. So now let me define what is an asymptotically ADS metric. Well, this is really what the words say. So the metric, as you go to large distances, it should look like this one, but it should differ at subleading orders. So then now the ADS boundary in this Z coordinates, so the ADS conformal boundary is Z equal to 0. And so on. So that's what an asymptotically ADS metric is. Now for ADS CFT, we need a further generalization to that. And this is so-called asymptotically locally ADS metrics. And this more general metric is the following. So the main difference here is this term here. So this is a general metric. So here we had in asymptotically ADS metrics, this was just a Minkowski metric, but here we replace this by a general metric. And in ADS CFT, this metric here will be the source for the dual energy momentum tensor. Okay. Now, before I move on to start setting up the dictionary, I want to discuss one more aspect that will become important. And this is this is how dilatations are realized. So now if you look at this metric over here, this metric over here, now it is clear that it has a symmetry, so isometry. So if you take Z to be some number times Z, and Xi to be a number times Xi, then you can see that the metric is invariant. Because the factors just cancel out. You can see you get, in both cases, you get yes, 2 powers in the numerator and 2 powers in the denominator. Now, this was a property of ADS metrics, but we want to understand how that extends to this more general class of metrics that does not have a flat metric over here. And the main point is that in this more general setup, actually, let me rewrite also this general, because I'm going to use it later. So let me also write the general metric in domain wall type coordinates. And this gamma ij is 2 times r, and then we have g0 ij, e to the minus 2r, g2 ij, and so on. And now the, the main observation is that if you look at the radial derivative, then the radial derivative acts like a dilatation operator of the dual theory up to sublimiting terms, up to terms of 4 the e to the minus 2r. And one way to see this is to just apply this, just the metric given above. So now, for example, if I act with a radial derivative on the metric, then when I hit this factor, I get a factor of 2. And then since it's an exponential, I get back the metric. And then when I will act on the factors inside, these are going to be suppressed relative to the leading order by a factor of e to the 2 minus r. And the same is true for all fields, it's not just for the metric. Now, dilatation operators act on the boundary metric by a constant Wald transformation with a weight 2. So this is a constant Wald transformation. So, and now if you compare this side here with that one, we see that indeed that we get what I just described. So the radial derivative acting on the metric is the dilatation acting on the metric up to sublimiting terms. And this is a property of this general metrics, and this means that you can use this dilatation operator in order to organize your computations in a covariant fashion. And this also geometrizes the normalization group flow. So, so this goes with the slogan that the kind of radial direction correspond to normalization group transformation, to a normalization group scale. Okay, so one will discuss the holographic dictionary who would want to understand the asymptotics in a way which is covariant with respect to the boundary theory. And the best way to do this is to use the fact that the radial derivatives, the linear order, act as dilatations, and then you can organize a computation according to eigenfunctions of the dilatation operator. Okay, so any questions on this? Okay, so I think we now finish with the preliminaries. So now we'll start with the kind of setting up the kind of holographic dictionary. And I will start with the kind of the main, the postulate of holography, the holographic relation. So in holography, again, we have D+1 gravity on one side, and we have quantum field theory on the other, and they're meant to be equivalent. So the main formula is the following. So we have the partition function of string theory in ADS on one side. So this is kind of, so to define the theory, we need to understand how the fields behave at infinity. So this is going to be a function of the boundary conditions we impose at infinity, plus possibly any parameters that appear. For instance, if you have at low energies, this will be described by some gravitational theory, which would depend on masses, coupling constants, and so on. So this is the one side of the duality, and the other side, actually now let me do it for CFT for this slide. So the other side tells us how to connect string theory on this background to something on the CFT. So on the other side, we have the expectation value. Well, we have the correlators of gauge invariant operators, where the field which parameterize boundary conditions on one side becomes the source for a gauge invariant operator on the other side. And this expectation value is evaluated on the CFT. Now, the CFT itself depends on a number of CFT data, which is the spectrum characterized by the spectrum of dimensions and OP coefficients. And this data over here should be encoded in this data that we have on the other side. So if we want to have a full dictionary, we need to understand how the parameters are mapped from one side to the other. And then the postulate is that this formula here is going to tell us how to compute. And the one thing that we already know that how it maps exactly from one side to the other is precisely that the source appears here and there. So here on this side appears as a boundary condition, and on that side it appears as a source for a gauge invariant operator. So now, of course, we still don't know how to do real string theory in ADS. So at low energies, then the string theory becomes some gravity theory. And then in that context, so the partition function here can be computed using a path integral. So we integrate overall fields with some action where the fields have boundary conditions at infinity. Now, in full generality, this is still not very easy to compute. But what has been done mostly in the last 25, 30 years is to further do a subtle point approximation to this object. So just compute 3 level. So at 3 level, we have that the on-shell value of the supergravity action as a function of the boundary conditions, okay, that should be equal to the generating function of connected graphs. And our main goal is to understand how to make sense of this relation and then how to compute this correlators by computing this object. Okay, so now once we have this, then we can say now the 1-point function of the dual operator would be the functional derivative of the on-shell action with respect to the corresponding source. And then if we want the 2-point function, then we need 2 functional derivatives. This is x. Okay, and so on. So that's the objective. So let's start try doing this, at least formally, to see how far we can go. So let's say, we have an action. So we integrate in d+1 dimensions. And this depends on Lagrangian, which depends on some fields. Let's call these fields generically phi. So this don't have to be scalar fields, but just to kind of get an idea of how this is going. So now here we can see that we need the variation of the on-shell action. So let me start by varying this action. And let me also assume that my action is a standard action with just quadratic standard kinetic terms. So now if I do a variation, well, I can have derivative with respect to the phi, delta phi, and then a derivative with respect to the just using undergraduate classical mechanics or variational methods. So now I can integrate by parts to isolate delta phi, because here again we need to differentiate so we get this standard field equation term, but we also get the bounded term. Now this term here is 0 on shell. Because this is just the Euler-Lagrange equations. So then from here, we see that before I do this, so now if you look at this term here, so if you recall, when you do Hamiltonian methods. So usually we defined canonical momenta by differentiating the Lagrangian with respect to the derivative of a field. So this is, sorry. This is a radial canonical momentum. So now from here we see that the variation of the on-shell action with respect to the field. Sorry, here I should have had. Is equal to the radial canonical momentum, or in other words, the expectation value of the operator is equal to the radial canonical momentum. Now, the trouble with this relation is that it's imprecise in one way and it's ill-defined in another. So it's imprecise because here on this slide, I told you that the source is the boundary condition at the field at infinity. And in this relation, I just used the entire field, not the boundary condition. So that's, in a sense, the way in which it's imprecise. But it's also ill-defined because this object, so pi, goes to infinity as r go to infinity, as you can see from the factor of square root of gamma that we have here. So this is an infinity due to the infinite volume of space-time. So what we're expecting is we're expecting to recover the one-point function of the dual operator. Instead, we got something which is infinite. Now, if you would try to do a similar computation on the quantum field theory side, then generically, when you do the correlators, you would also find infinities. But in these cases, we have learned over the last 50 to 70 years how to deal with these infinities. So these are dealt with renormalization. So this infrared, so this is an infrared infinity here. This infinity is an infrared because it's due to the infinite volume of space-time. So bulk infrared divergence is more or less the same as the boundary UV divergences. And this we deal with renormalization. And now the question is how to do this, and this is what holographic renormalization does. Okay, so what I will do in the remaining of today's and tomorrow's lecture is work completely one example. But before we do this, any questions? Okay, so most of the existing lecture notes out there, they usually discuss scalar fields. And scalar fields are fairly easy because one doesn't deal with many of the technicalities. One has a lot of indices. At the same time, this is already out there, so you can go and read some of the other lecture notes. So what I want to do in this. So I guess I have another. How long do I have today? How much longer do I have today? Another 10 minutes?
You have 10 minutes.
10 minutes, yes. So in the remaining 10 minutes today, I will start introducing the computation, and then we'll finish it tomorrow. So what I want to do is the aim of the remaining lectures is to compute the 2-point function of the energy momentum tensor in D equals 2. And I will do this completely, given all details, or almost all details. But I will
You have 25 minutes, not 15.
25 minutes, okay. So I will do this completely. So we'll start today and finish tomorrow. But the introductory part will be valid for gravity in all dimensions. So for gravity, the corresponding object, the radial canonical momentum, is related to the extrinsic curvature, and I will introduce that in a moment. So I'm just going to give this formula here, and then we're going to go and explain it in a lot of detail. So Kij is the extrinsic curvature. And 2 kappa square is related to the Newton constant. Okay, good. So now we're gonna have a bit of parenthesis where I described a little bit the geometry of embedding surfaces in space-time. So suppose we have a manifold M with metric G mu nu, and I want to foliate this with hypersurfaces. So first, hypersurface which I would call sigma r, is defined by giving a relation so we have r, so given some function r of x, and then once we have a happy surface, we know how to compute the unit normal. I mean, that's in undergraduate calculus. So essentially is the gradient. So the unit normal is obtained by taking the derivative for this function. And then if I want it to be unit normal, then I divide by the norm. So let me sketch this a little bit. So this is my hypersurface at r equals r naught. So I will call this sigma r naught. And at some later position. So usually in GR, this is described in terms of time foliation, but for our discussion, we have a radial foliation. So we have radial foliation. This radial foliation is described to have a radial flow, which is described by the equation x nu d mu r equal to 1. So this radial flow is given by, if you have this curve here. Now the normal to this curve is x mu. And now this x mu, you can now, so we also have a normal to the surface, eta hat mu. And then you can project this down as well. So now from here, we have, so the x perpendicular is proportional to the unit vector. So this n is called a lapse. And then you have the x parallel, which we would call n nu, and this is called a shift. So this, in sense, defines the geometry as the hypersurfaces move from one place to the other. Then we can follow. So in GR, this curve would be kind of a time function. In our case, is a radial function. And as we move from one radial position to the other, then we have this curve may not be straight, so we have a shift and a lapse. Now, once we have such a hypersurface, we can also define an induced metric on that, which is a metric induced from the bulk. So the induced metric is the bulk metric minus twice this unit vector. So now we know there is a metric in that surface, but the surface here is also embedded in the d+1 dimensional space-time, and we want to know how is this embedded. And the way this is embedded, this is described by the extrinsic curvature. So the extrinsic curvature is given by the covariant derivative of the unit normal. And yeah, so that describes how the surface is embedded. Now, once you have these hypersurfaces, there are also relations between the geometric.
Kostas?
Yes.
One small question.
Yep.
Is this covariant derivative the one in the d+1 dimensions or the one on the surface itself?
That's in the d+1 dimensional, but I mean this object here defines what is the covariant derivative along the surface. So you have the bulk object, and this projects and this projects this bulk object to the surface. So this sometimes people call this kind of d nu to indicate. So now that's and let me put a hat as well. That's an intrinsic. That's the object that has covariant derivative along the surface. Of course, you also have, so we have a Levi-Civita connection of the intrinsic curvature. I have curvature tensors, and these objects are related. So the objects you define in the bulk are related to the objects we define intrinsically on the surface and the extrinsic curvatures. And these are called Gauss-Godacu relations. I think I misspelled Mr. Godaci. So if you have the bulk curvature, if you project it to the surface, So you contract all indices with the induced metric. Then this gives the curvature of the induced metric plus pieces that depend on the extensive curvature. And let me see. Yeah, and then there is also a relation that involves the Ricci, where now we are contracting one index with a normal and the other with induced metric. And now this gives the covariant derivatives of the extrinsic curvature. Now, using these relations, one can then rewrite Einstein equations in a way which is adapted to the foliation. And this is the format that we use in order to normalize the theory. Now, this is completely general, but for our purpose, we would like to work in this coordinate system I defined earlier, where I had the asymptotically locally ADS methods. I want to work with kind of this coordinate system. And this coordinate system has the property so that the radial direction, so you can see there is no, so let me put it here, no dz dxi piece, and then the coefficient dz square over z square is 1. So this is a defining property of the so-called Pfefferman-Graham cage. And I would like to work in this frame because the holographic formulas would be simplest when we work in this coordinates. There is another way to describe these coordinates by saying that we want to use Gaussian normal coordinates at infinity. So, and this means, actually before we move this, I should have given this. Let me move this a bit down. So now, once we know the foliation, so the metric can now be written in a way which is adapted to the foliation. So the metric we started from, now we can write it as gamma, which is the induced metric on the surface, and then we have pieces that mix the two. So we have the shift in the lapse now under. So now if we now go to Gaussian normal coordinates, this means that we set the shift to 0. And the lapse to 1. And then in this coordinates, now the metric comes this one. And this is precisely the metric in this that I used earlier in kind of the domain wall coordinates. Yeah, so this is this form of the metric. So now we're gonna further specialize into that. Yeah, let me see how much. So now, once we have these Gauss-Godacu relations, this one's here, we can rewrite them a little bit. So Gauss-Godacu, for instance, if I trace this equation twice, if I trace it over all indices, this one, then I have, so then one can see that, okay, let me write it and then I'll explain it. That's what we get if you trace these equations over the indices. You can see you get k squared and k squared, and then the rest organize these Einstein equations. So when Einstein equations hold, so this is the Einstein tensor. So and then the Einstein equations. In our case, means that we have where this is the cosmological constant.
So Kostas, you're doing pure gravity right now and not the full domain wall?
Yeah, so now I'm gonna, so far it was completely general. And now for the remaining of today's lecture and tomorrow, I'm gonna restrict to just pure gravity. So if I will have matter, I can do all of what I'm gonna describe. It goes through completely unchanged. Of course, the formulas will have additional terms, but at this stage, instead of just using here, instead of using this relation here, then the right-hand side would contain the matter energy momentum tensor, and that would enter in the relations. But all the rest will be the same. So now if we impose Einstein equations and go to Gaussian normal coordinates, then this equation here now becomes and then there is a similar equation that comes from this one. Let me get an equation.
Kostas, can you go back?
Yep.
The units don't match
Yeah, so I have set the ADS scale to, so okay, let me put it right here. So I set the ADS scale to 1.
So lambda is 1?
Yeah, lambda, so capital lambda is minus the E minus 1, 2. And
okay.
then the ADS radius is equal to 1.
Okay, thank you.
Yeah. Then we get that equation. And finally, there's a dynamical equation. Yeah, let me first give it in a general form. So, so if we take the lead derivative along this normal direction of the extrinsic curvature, Then again, one can use the description of hypersurfaces I gave earlier to show that this holds, this formula holds. And then we can go to 39 gram coordinates. And then this relation here becomes okay, so now these three equations, which I'm now going to put also in the box, this one, and this one here, these are equivalent to Einstein equations. Now, but now written in a way which is adapted to this radial foliation. And now our task, so if we want to do ADS-CFT, now we need to solve these equations and evaluate the action on shell.
Okay, so Kostas, you have about 5 minutes. So
yeah, I think we are wrapping up, and then I'll start tomorrow by saying how to solve it. But now if we go back to what I was describing earlier, so now earlier I told you that the radial canonical momentum, and now you can see why this is a radial canonical momentum as well, because actually, so if I work out, okay, before I write this, so in Pfefferman coordinates, then the extrinsic curvature is just the radial derivative of the metric. So it is like a radial canonical momentum. And then the actual canonical momentum that you get from the action is again given by this expression. And now if you, so let's say now we're in d equals 2, because what I mean, I will restrict myself to d equals 2 to make the computations easily describable. Then the square root of gamma behave like this. Then Kij go like that. So in for general D, it will go like into the dr. And then you can see that this formula diverges. So what I will do tomorrow is understand how to remove this infinities. And I will describe how to do this using this kind of covariant language with the radial canonical momentum. Okay, I think that's a good time to stop.
Okay, thank you.
Questions?
Any questions from the audience? Okay, I think people want coffee. So we're going to have a 15-minute break, and then there's going to be a discussion in 15 minutes of the talks of the day. So if you can stick around, we would like that very much. But if you can't, then we understand. Okay. Thank you. Let's